Let's work out the structure of a white dwarf. The white dwarf is supported by hydrostatic equilibrium still, so you can write the equation hydrostatic equilibrium. Gravity is supported by the pressure, except that now the equation of state is that of a degenerate gas. That's the only difference between this and a star of an ideal gas. Now, let's make an approximation of a constant density so that we can substitute the mass in the shell by the density. We can integrate this equation from p equals 0, which is at the surface, until an arbitrary radius r inside the white dwarf. What you find then is this relationship for the pressure inside the white dwarf. So we can solve it for the center, set r equals 0, little r equals 0, then you have the pressure at the core. From this, you can derive the famous Chandrasekhar limit for the maximum mass that a white dwarf can have. Let's take first the non-relativistic limit, where the pressure is proportional to the density to the power of 5/3. So we can equate this pressure to the pressure found for the core. And now we can solve for the radius. This yields. So the 6th power of the radius is proportional to the inverse of the density. Now substitute the density for the mass. What you find then is, now if you eliminate this cube of the radius on the right hand side, by this 6 here becomes an r cube. What you have then here is, if you multiply both sides by the mass, the cube of the radius times the mass is equal to 4 pi times the cube of this quantity in the parentheses, 3k1 over 2 pi g. And what is in the right-hand side are constants. So we found the relationship between the mass and the radius. Since the cube of the radius is proportional to the volume, you find the mass-volume relationship for the white dwarf. The mass times the volume is constant. So that proves that the mass-radius relationship that I showed before in the beginning of the video. As a white dwarfs gain mass, it must shrink. More massive white dwarfs are smaller. This is expected because as you add mass, the star must increase the pressure to provide support against gravity. And in a white dwarf, the pressure is a function of the density. The electrons must be more closely confined to generate the larger degeneracy pressure to support a more massive star. Now this works up to some point. As you know, there are non-relativistic and relativistic limits for the degenerate equation of state for the pressure. As the electrons are packed even more closely together, because of Heisenberg's uncertainty principle, that implies that their velocities are increasing. And at some point, the velocities are going to become close to the speed of light. They're going to become relativistic. Let's see what the implication of this change in the velocities from non-relativistic to relativistic will have for the structure of the white dwarf.